Okay, so yesterday we spoke about boundary layer flow. I said I'll go over it before we continue. Right, so yesterday we spoke about what boundary layer flow is. We spoke about this diagram. I think that's where we ended it. So we talk about all these things today, and then we'll continue with the overall mass balance. Now, we said the boundary layer is the region near a solid where the fluid motion is affected by the solid boundary. So please take note of this, right? The point where the motion of the fluid is affected by the solid boundary. Okay. So when the fluid flows over the surface, the elements in contact with the surface should be brought to rest. So we spoke about that. And then we said the adjacent layers will be retarded by the viscous drag of the fluid. So the velocity in the neighborhood of the surface will change with distance perpendicular to flow. So remember we spoke about the fact that when a fluid is flowing over a solid surface, the particles just above the solid surface, right, will not be moving. They will be, or they will adhere to the solid surface, or they will be stuck to the solid surface. Then the ones just above them, their flow will be retarded, or it will be slowed down because of the one below it. So you can even see from the animation here that the one above has a higher velocity than the one below. The one below will be slowing down the one above, right? So that is what the boundary layer, and that's when the boundary layer comes in. So when we talk about the boundary layer, we're looking at a region in the fluid where this solid boundary or where this solid part is going to cause an effect on the motion of the fluid. Okay. So would use this diagram to really explain that a bit more, right? Yesterday, what we're seeing was that for this diagram, if we should look down here, we realize that the velocity over here just at the surface is zero, right? And then we also made mention of the fact that as the fluid continues to flow, the ones above are going to have their velocity reducing. So there's some form of retardation that is happening until it gets to a point where their velocity is almost zero. Right? So we use this example that if we have a football and we kick it over a rough surface, what's going to happen is that eventually it's going to slow down and stop. The reason is that there's frictional force between the ball and the ground. So the ground is retarding the motion of the ball. In the same way, the layer below is going to retard the motion of the layer above. So if we look at this, you realize that there's a certain broken line here. This broken line here is showing the region where the solid surface is going to affect the fluid flow. So this is what we mean by that. We also did this illustration. So everything here, this entire area here, right, is the fluid. And what we were saying yesterday was that the fluid has a certain velocity that it is moving with. So over here, the velocity is fixed. It's one velocity, right? Every layer has its velocity. But then it gets to a point where when it touches this line, what it means is that the effect of the layer below can now be seen or can now be felt. Is that okay? So the layer below is going to slow down or retard the layer above. That layer is also going to retard the layer above it. Is that okay? So if one layer is retarded more, it gets to a point where it can also retard other layers more. Right. So what we're just trying to say is that the fluid particle at this point is going to be moving with a constant velocity. But when it gets to this broken line, which we call the hydrodynamic boundary layer, what's going to happen is that its velocity will now start being retarded. Is that okay? So the hydrodynamic boundary layer is just a region in the fluid that is that where we can see the effect of this solid wall. So remember we said that it's the region near the solid where the fluid motion is affected by the solid boundary. So this region down there, this is where the motion of the fluid is affected by the solid boundary. It is in this region that we would see the velocity of the fluid being reduced. But then above it, the velocity seems almost constant. And remember, we spoke about what we call ideal flow or potential flow. And we said that when we are above the hydrodynamic boundary layer, we can assume that we are working with ideal flow. So you realize that if you look at the velocity profile, right, you can see that the velocity reduces. You can see the arrow here is smaller than the arrow here. But when it gets above the layer, the arrows are almost the same length. So the velocities are literally the same at those points. Is that okay? So that's what the boundary layer is. It's just a region within the fluid where we can see the effects of the solid wall on the fluid. Now, when we talk about hydrodynamic, we are looking at the forces in the fluid. So we know that the forces that are going to retard, and we talked about it yesterday, that we can also have a thermal boundary layer. So that's where we see the effect there of the wall, right, on the heat characteristics of the fluid, so on the temperature of the fluid. So if we're working with a thermal boundary layer and not a hydrodynamic boundary layer, what we realize is that the wall here has its own temperature, and its temperature will affect the temperature of the fluid here. But once we cross that boundary layer, the temperature of the fluid is fixed. It's not going to change. It's not going to be affected by the wall anymore. So it's like I might have a wall. Maybe the wall is at 50 degrees Celsius and my fluid is at 20 degrees Celsius. What we are saying is that there's a point up to which the temperature of the fluid will change because of the temperature of the wall. But then we can go far enough such that the temperature of the fluid will still be 20. We can progress. Is that okay? So that's the whole concept behind the boundary layer. So we are saying here that suppose a fluid with uniform velocity approaches the plane surface. So V4, that's the velocity up here. Right, that's the uniform velocity V4. That's what we have up here. So that's V4. When the fluid reaches the surface, a velocity gradient is set up because of the viscous forces acting within the fluid. So that's the velocity gradient. You see that there's a change in the velocity. It's very small down here, and then it's large up here. If there was no boundary layer or there were no effects of the boundary, then the velocity profile would be this way. So all the velocities at every point are the same. There's no retardation, there's no um, slowing down of any layer or anything of that sort, right? Then we also say that the fluid in contact with the surface will be brought to rest. So we spoke about that. It will gradually approach the free stream velocity at some distance from the surface. So what we're saying is that the fluid at the surface is going to be brought to rest. That's zero. But the way we move sufficiently away from the surface, what's going to happen is that the velocity of the fluid there will now approach the velocity of what the fluid was originally coming with. That's what we call the free stream velocity. The velocity of the fluid that's not being affected by the boundary. Is that okay? So the velocity profile, realize that it starts at zero and it gradually increases. So we can see the length of the arrows increasing. The length of the arrows are indicating the magnitude of the velocity. So we see that we start at zero and it gradually increases. When we get sufficiently far enough from the wall, we can now start approaching the velocity here. That's the free stream velocity, the velocity that the fluid was originally coming in with. Is that okay? So we said that we can divide the flow region into two parts. We can have what we call the non-viscous region. That's away from any solid surface. And that's where we have what we call our ideal fluid, or where we have our ideal flow. So we assume that viscosity is zero and density is constant. So that's going to be this region over here, the region above the hydrodynamic boundary layer. So we can call that the non-viscous region, because that region is behaving as though it didn't have a viscosity. The velocity is constant. So the viscosity is zero, the density is constant, right? And we can have the boundary layer. So that's the region here, right? And that's the layer where the fluid would be sticking to the surface because of viscous forces and will be affected by the solid boundary. In this case, it's our wall. Okay. So we are seeing that the thickness of the layer in which the fluid is retarded becomes greater with distance in the direction of the flow. And this layer was termed boundary layer by Prandtl. Right? So we can actually see it here. That's the thickness of the layer increases. When we start, it was just one layer of fluid that was retarded, the one that was just at the surface. But then as the fluid continued to flow, it was affecting the layers above. So we realize that the layers continued to grow because now the layer below, as it's being affected, it gets to a point where it also now starts affecting the layer above. So the thickness of the boundary layer is going to increase. Realize that it starts very small here, but then when it gets to this point, it's quite it's quite a distance or it's quite thick compared to when we began. Okay. Then the other point is saying that anywhere along the plate, the velocity profile changes from the uniform stream profile. Right. So if we are along this plate, the velocity profile is going to change. Is that okay? Then the velocity increases from zero at the surface to nearly the free stream value at some distance away. So we spoke about that. The fact that the velocity starts from zero here and then it increases until it gets to the point where it reaches the boundary layer. When it crosses it, it now has the stream and the free stream velocity, the velocity of the stream that's not affected by the layer. Right. Then we are saying that the free stream velocity is approached asymptotically, and therefore the boundary layer strictly has no precise outer limit. So it's convenient to define the boundary layer thickness such that the velocity at its outer edge equals 99% of the free stream velocity. So let's talk about that a bit, right? If we say something is approaching asymptotically, it means it is approaching it, but it never actually gets there, it never actually meets it, right? So the free stream velocity, if we look at this diagram, what we are saying is that this boundary layer, right? If we look at the velocity profiles, just below the boundary layer, we can get very, very close to the free stream velocity, but we can never actually get to the free stream velocity. So what we can define is that at the outer edge of the boundary layer, so that's just where the broken line is, at that outer edge, because we can never actually approach, or because we can never actually get to the free stream velocity. Our maximum velocity we can reach should be 99% of that. Right? So that's why we are just saying that it doesn't have a precise outer limit, but then we can define the boundary layer thickness so that the velocity at its outer edge is 99% of the fusion velocity, right? So the hydrodynamic boundary layer thickness represented with delta, and that's the point where Vx, that's the velocity at any point, is equal to 99% of our fusion velocity, which represented with V4. Is that okay? Then within the boundary layer, the velocity in the x direction is going to vary only with um, the distance, that's y. So such that the velocity is a function of y. So what we are trying to say is that the velocity, right, is going to be a function of the distance, the vertical distance. Is that okay? Hello? The velocity is going to be a function of the vertical distance. But realize that as we are moving vertically upward, the velocity is going to increase. Is that fine? So it's very similar to what we spoke about when we were considering the Newton's law of viscosity. Then we derived a formula for our shear rate where we had the change in velocity with respect to the change in the y direction, right? So the velocity is going to be affected by the vertical distance. That's the change in the y direction. Unless as we are moving up, the velocity is changing. Okay. And please, can you all hear me? Please, can I be here? Hello. Please, can I be here? Please, whoever is on the screen, please stop. Okay. Okay. I think we just take it from there. Just continue from there. So we are seeing that as the boundary layer thickens, at distances further from the leading edge, a point is reached where turbulence appears. The onset of turbulence is characterized by a sudden rapid increase in the thickness of the boundary layer. So this is what we are seeing. When the fluid is moving, right, this is the boundary layer, I realize that the thickness is going to increase. Initially, it will start as laminar, but it gets to a point where we now start seeing turbulence coming in there. And that onset of turbulence is characterized by a sudden rapid increase in the thickness of the boundary layer. So in the turbulent region, we have what we call a laminar sublayer near the surface. What we are trying to say is that if this is the graph we are considering, right? What we are saying is that when it starts out, this side may be laminar, right? This whole portion here may be laminar. But then this part here may be turbulent. But then even in the turbulent region, when we are very, very close to the surface, that layer, just that thin layer down there can be laminar. So that's what we are talking about the laminar sublayer. Okay. So you said in the turbulent region, there is still a laminar sublayer near the surface. So the change from laminar to turbulent fluid in the boundary layer will occur at different distances downstream, depending on the roughness of the surface, the physical properties of the fluid. So what we're just trying to say is that the points where it now starts changing from laminar to turbulence depends on the characteristics of the fluid and then the characteristics of the surface the fluid is flowing over. I think we'll see that very soon when we speak about Reynolds number. So this is what we were talking about, right? So this is our boundary layer. And then realize that it starts out laminar. There's a transition region where it can switch between laminar and turbulent. And then this part here is the turbulent layer. Now I realize that there's a certain sublayer. There's a certain where the broken line is. We call that the laminar sublayer. So just up to that line from the surface, you can expect laminar flow. But then it's very, very thin. It's like very, very small. So we say that the laminar boundary layer becomes unstable due to some disturbance. And the disturbance forms unstable waves in the laminar boundary layer, which grows into eddies and then a turbulent boundary layer. Right. So what we are just trying to say is that there's a laminar region here. It starts becoming unstable after some time. Then it forms eddy. So we can see an eddy being formed here. And then it moves into turbulence. That's what they're just trying to say, right? I think that some common disturbances that can cause it to move from laminar to turbulent are pressure gradient, surface roughness, heat transfer, body forces, friction disturbances, right? So pressure gradients, if we have a region that has a higher pressure, a region that has a lower pressure, those cause material to move faster or with more force in that direction, which can introduce turbulence. If the surface of a material is rough, can introduce some turbulence. If there's heat transfer, it also affects the kind of movement in our system, right? Because there will be convective currents and all those things. Body forces are just looking at the forces within the fluid. And then the friction disturbance is um, the kind of disturbances that can occur as the fluid is just moving on its own, right? So these disturbances can grow to form um, the turbulence boundary layer, a layer where we can see turbulence being prominent. So the turbulence boundary layer, we can divide it into three regions. We can have the viscous or the laminar sublayer, the buffer layer, then the turbulence layer. So it's basically almost like laminar transition and turbulence, but then it's happening in the turbulence region itself. So what we are saying is that if this is our turbulence region, just this portion here, right? Just below it, just at the surface, we have a laminar layer. Then just above the laminar layer, we have a region that is almost like a transition region. So we call that the buffer layer. So you can have it switching from laminar to turbulence, laminar to turbulence. And just above that, it is purely turbulence. So if we continue, realize that they said the viscous sublayer represents a very small portion, the turbulence boundary layer. That's just at the surface. It's extremely small. Usually, it can even be less than 1% of that whole region. The buffer layer represents about 15% of that region. So the region where we see it switching between laminar and turbulence. Then the turbulence layer itself can represent about 85% of the entire region. So that's this portion here, once again, the turbulent region, just at the surface, right? It can be less than 1%. That part can be laminar. And about 15% of that region would be a point where we have a switching between laminar and turbulent. And then just above that buffer layer, we can have it to be purely turbulent. So that's about 85% of that region. Now, most technical flow processes are best by considering the flow stream as two parts. When we want to steady flow, as we can consider the flow stream as two parts. We can consider the boundary layer, we can consider the remaining fluid or the free fluid, right? When you're looking at flow through pipes, I think that the boundary layer will fill the entire channel. What we are just trying to say by that is, if I have a pipe, right? Or let me start it this way. If I have maybe a surface here, realize that we said that boundary layer is going to go like this. Right? Let's say if I have a pipe, I have two surfaces. There's going to be another boundary layer at the top here. So what they're trying to say is that there's a point where the boundary layers meet. There's a point where all of the fluid is going to be affected by the surface. So when the boundary layers meet, everything after it, right, is going to have an effect coming from the solid. Because remember we said the boundary layer is a point where the fluid is affected by the solid surface. Okay, I'll slow down. Okay. So we said the boundary layer is the region where the fluid is affected by the solid surface. So once again, if we have yeah, over here they're saying that in flow through pipes, the boundary layer fills the entire channel. So we have one surface down here, and this is a boundary layer that is formed by that surface. Then we have another surface up here. This is a boundary layer formed by that surface. When it gets to a point where the boundary layers meet. So if the boundary layers have met, it means everything after the boundary layer is going to be affected by the surfaces. Then the parts here, the parts before, is not going to be affected by the surface. So its velocity is the same, its viscosity is not going to be affected, nothing of that sort. Okay. Now, boundary layer separation. So this is another term we need to know. Boundary layer separation occurs when the boundary layer travels far enough against what we call an adverse pressure gradient, and the speed of the boundary layer relative to the object falls almost to zero. So I'll explain that very soon. I think we have a slide for that soon. I'll explain that very soon. The fluid flow becomes detached from the surface of the object. So please note that, right, for boundary layer separation, the fluid flow becomes detached from the surface of the object, and it will instead take the form of eddies and vortices. The flow separation can often result in what we call increased drag. So now we'll talk about drag and then we'll talk about boundary layer separation. Drag is just the force that acts parallel but opposite to the flow of the fluid. And it does this to slow down or retard the movement of the object. So if you look at the first diagram, we have a plane moving through air. Now air is moving in this direction. And there's a force that is going to push the plane backward. That's drag. So these are forces around an object. If there's a force that is retarding the flow of the solid components in the fluid, that's going to be drag. If there's a force that's going to push it or increase it, that's thrust. If there's a force that is going to pull it down, usually that's going to be the weight of the material. And if there's a force that will pull it up, that's going to be a lift, right? But we are just interested in the drag force because our fluid is flowing in the direction of the thrust, but then the drag is retarding it. Right. When we talk about boundary layer separation, we said is the point where the boundary layer gets detached from the solid surface. So if you look at this image down here, we can see a very thin boundary layer. And there's a point where we see it bent and then increase sharply. That bent, then that bent point is what we call the separation point. That's where we have what we call the adverse pressure gradient. So the pressure gradient becomes so significant that it will cause the boundary layer to just separate from the surface. So realize that over here, usually you won't even see material fluid there. Or sometimes the material you see there would have some kind of eddy or some kind of vortex being formed. So let's talk about eddies. So if you look at this image here, right, realize that there's a very thin boundary layer at the top. But then if you look at it critically, there's a certain region that is dark, there's no material there. Then we can see this eddy being formed here. That's boundary layer separation. So the fluid is moving over the surface, but then it's gotten to a point where now the boundary layer just separates from the surface. So we can see this dark region where there's no material there. But we can now just start seeing some kind of eddy, some kind of turbulence forming in there. Now let's look at this animation. I think it will help us a bit too. Okay, so this animation over here. Like as this what we call an airfoil, realize that we can see the boundary layer being separated from the surface. Initially, when it is this way, we can see the very thin boundary layer. That's the part that is just at the surface here. But then we can see that it now starts to separate as we start to turn the floor. So there's a region where we don't see anything at all. It's starting to separate from the solid surface. That's boundary layer separation. And what happens with boundary layer separation is that it causes increased drag. So the force that is going to retard the motion of this object is going to increase. Is that okay? So that's it for boundary layer separation and for drag. So we are about to speak about Reynolds number. Before we go on, are there any questions from what we're talking about with respect to the boundary layer separation and drag? Are there any questions? Any questions? Oh, are we here? Okay. Hello. 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 Okay. Can I be here? Hello. Okay. If someone is asking that I should repeat the part on the boundary layer separation, sure. So what we're saying about the boundary layer separation is that realize that for our boundary layer, there's going to be, so this is a solid material moving through a fluid. So let's look at this image down here, right? There's a very thin layer, which is a boundary layer, just at the surface here. But gets to a point where now that layer would input gets detached from the surface. So where the boundary layer is, there's still some fluid there. So if you look at this animation, realize that as the fluid, so the lines you see here are just showing where the fluid is, right? As the fluid is moving over this solid material, just here, this is the boundary layer, right? That's the boundary layer. It's still attached to the surface. There's still some amount of fluid there. And then as it continues to move, realize that it gets detached from the surface. So realize that there's a point where now it is no longer even attached to the surface anymore. So if you look at it critically, you realize that now it gets to this point, this region here is no longer attached to the surface. That's the boundary layer separation. The boundary layer has become detached from the surface. And what we end up seeing is this kind of turbulence being formed. Is that okay? So it happens when we have like very large pressure differences across the solid surface. Is that fair? So boundary layer separation is just the point where the boundary layer separates from the solid surface. And over there, we won't really see any fluid there, but we can see some kind of turbulence or some kind of eddies being formed. So if you look at even this image down here, realize that this region here, this dark region here, there's no fluid here. And then we can see some eddy forming at that point. Is that okay? Okay. So okay. So we can look at Reynolds number now. Okay, Reynolds number is very important. Yesterday, someone said I said it's not important. Please, it's very important. Okay. Reynolds number um, is what we use to determine whether we have laminar or turbulence flow. So Reynolds studied the conditions under which one type of flow will change into another. And he found out that the critical velocity at which laminar flow change into turbulence flow depends on four quantities. Yes, so the boundary layer separate. Someone is asking another, okay, at high velocity. When you have very high velocity, you can have, yes, you can have boundary layer separation happening. When the velocity is very high, yes. Okay. So Reynolds studied the conditions under which one type of flow will change to another. So when we have laminar flow, study the conditions under which it can change to turbulence flow. And he found that the critical velocity at which laminar flow changes into turbulence flow depends on four quantities. So these are the things he realized affect the flow that will cause it to change from laminar to turbulence, right? When we say critical velocity, or when we say critical or anything, we're just talking about a particular value where something now begins to change. So even if we talk about a graph, talk about a critical point, it's more like a turning point where we can now have some kind of change happening, right? So you realize that there's a certain velocity at which laminar flow will now begin to change into turbulence flow. But then if we consider other parameters as well, we realize that they also affect the transition from laminar to turbulence flow. So he realized that the diameter of the tube, right, would affect it. The reason why we put characteristic length here is because it may not necessarily be a tube you are working with. So the characteristic length is just looking at the length or the dimension that is going to affect the flow. If it is a tube, it is the diameter of the tube. Is that okay? If it is a flat surface, then it's not going to be the diameter. You can't see the diameter of a surface or the flat surface. So it will be the length of the surface. If it is a sphere, then it can be a certain relation. So maybe the diameter of the sphere or maybe the radius divided by 2. There are some relations for those things to find what we call the characteristic length. Is that okay? So the length or the dimension that actually affects the property we are working with or the system we are working with, right? So for a tube, it will be the diameter of the tube. Then you also realize that the viscosity affects the, I think there's a question. Yes, high pressures and then high velocities as well. So the viscosity also affects whether it would be laminar or turbulent, then the density as well, and then the average velocity. We've already spoken about the velocity. So he realized that if we combine all these factors, we can get something that's dimensionless. So Reynolds number is just the density, the velocity, then our characteristic length, which in this case is the diameter of a tube, divided by the viscosity. This was the relation he came about, right? So if we calculate this, what we are finding is what we call Reynolds number. Now let's look at why it is important. The transition from laminar flow to turbulent flow may occur over a wide range of Reynolds numbers depending on the conditions. So when we have ordinary conditions of flow in pipes, right, Reynolds number being less than 2,100 will give us what we call laminar flow. So what we are just trying to say is that if I should calculate Reynolds number and I get a value less than 2,100, then it is laminar flow. If I have a value between 2,100 and 4,000, then that's a transition region. And if I have a value above 4,000, and that is turbulence flow. Realize I highlighted ordinary conditions and flowing pipes because you can have different systems. So the value at which you would have laminar flow can be different. You might have a system where laminar flow would occur up to maybe instead of 2,100, it can be maybe up to 10,000, right? So it depends on the kind of system you have. But then when we have ordinary conditions and normal temperature, pressure, our pipe is smooth, all these things, right? And it is a flow through a pipe. Then we can work with these values. So these are just very common values we use, right? But then if you look at the points here, see that for flow over a flat plate, transition usually occurs over a range between 2 times 10 to the power 5 and then 3 times 10 to the power 6. And it doesn't only occur at a single point. So flow over a flat plate is not working with the values you use for pipes. Just take note of that. The values that you would use will depend on what you're dealing with. If it is a pipe, if it is a flat surface, if it's even a sphere. So if you look at the last point here, see that for flow around the spherical particle, the flow is laminar if Reynolds number is less than 1, right? So someone might ask that, how will you know which one to use? Most of these things are already been done experimentally, they've been calculated. So if you are supposed to use them, the data will be provided, or you can make references. So these things are available on the internet, they're available in different materials, right? So maybe I'm dealing with a particular kind of pipe, and I know, or with a particular kind of fluid, a particular kind of system, I will know which values would give me laminar flow, which values would give me turbulence flow. Is that okay? So the transition to turbulence flow and then the degree of turbulence intensity depends on some factors. It depends on the kinetic energy of the mean flow, which is an indication of the ability of the flow to supply the energy that makes up the random turbulence motion. This is what we are just trying to see. Whether kinetic energy is highly dependent on velocity, right? So if we are having an increase in velocity, then we are going to have a larger Reynolds number. And what they're trying to say by that is that the kinetic energy, right, is an indication of the flow to supply energy that will make up the random turbulence motion. So if you're having a higher velocity, you're going to have a higher kinetic energy in the system, and a higher kinetic energy is going to contribute to turbulence. Then the point two say that the dissipative effects of the viscous force is that the viscous work done on the mass, right? So this also affects our degree of turbulence. So the viscous forces damp or dissipate the turbulence or eddy motion. This is what it's trying to say. The viscosity is rather going to reduce Reynolds number. So if we have something that is more viscous, because we are divided by a larger value, then we are going to have a reduction in the Reynolds number. What the addition says is that a larger viscosity is going to reduce the amount of turbulence you can get, right? So the dissipative effect of viscous forces means that the viscous forces are going to reduce the Reynolds number. And these values, the viscous force are going to damp or dissipate the turbulence or eddy motion. So if the system has a higher viscosity, right, the amount of turbulence it will have to be lower than a system that has a lower viscosity. In the last one, looking at the physical confinement of the fluid. That's the boundaries within which the flow occurs. So if you look at it, the physical confinement has a lot to do with the diameter. If I have a system that has a larger diameter, right, then the confinement is larger. If I have a smaller diameter, the region within which my fluid is confined is smaller. Is that okay? So if I have a larger confinement, then I'm going to have more turbulence. Okay. Now, we want to look at the physical meaning of Reynolds number. So we'll need to do a few calculations. So we'll build up to something and then we'll wrap up with this, right? If we consider the rate of kinetic energy moving through an area that is normal to the pipe axis, right? We can use our formula. So we know that kinetic energy is 1 over 2 mv squared. Now, we know that this mass here, remember we said if we have a property with a belt on top, it is a rate. So we know that this is our mass flow rate. It's mass over time, right? And we can also find what we call the volumetric flow rate. We are representing that with Q. So that's going to be volume over time. But we know that volume is also area times length or times a certain distance. And if we're having area times distance over time, we can make it area times velocity, right? So we are building up to something. Now, we also spoke about this when we were looking at CPC. We said that density, we can relate it to mass over volume. But if we are using mass flow rate and volumetric flow rate, we can relate it to mass flow rate over volumetric flow rate. So that's what we've done here. And then we can make the mass flow rate the subject to have density times the volumetric flow rate. But remember, we said the volumetric flow rate is area times velocity. So that's what we just done here. Mass flow is density times volumetric flow. And then volumetric flow is area times velocity. Right. Now, if we put the value for mass flow, what we've done here, which is equal to this, if we put it into this expression here, right, we'd end up with this last expression, the one that is in the red box. Okay. Now, we can also look at what we call the work rate of viscous forces, or what we call the shear stress work rate. So we'll talk about that. We know that our shear stress, right, is equal to our shear force over a certain area. So that we have Fs over A to give us shear stress. So we spoke about that yesterday. No, we spoke about that for lecture 1 as well. The formula for shear stress, right? And then we also spoke about, if we make the shear force the subject, then we have A times our tau, our shear stress. Now, to get it as work, we can multiply by distance because you know that work is force times a certain distance, right? But then we also want it as a rate. So to get it as a rate, we'll now divide by time. If I multiply my force times my distance and divide by time, I'm going to get what we call the shear stress work rate. So it was a shear stress, right? And now it is a kind of work, and then it is per time. So we call it the shear stress work rate or the work rate of the viscous force. So we see here that this is going to represent our viscous forces, and then there's a certain work we are doing from it, and then we are having it as a rate. If you relate it to the shear stress, that's the tau, then we can call it the shear stress work rate. So that's the formula for it down there, right? Now, we know that d over t, the distance over time, is velocity once again. So I can change that to Fs times velocity to be equal to A tau times velocity, right? And remember, we also said when we're looking at Newton's law of viscosity, that tau is equal to our viscosity times our velocity over a certain distance. So we can represent tau with this, right? So this was going to be a velocity gradient. But then we've taken it as though we've done the integration. So we have viscosity times velocity over a certain distance. Okay, so if I should replace tau here with this expression, we end up with this expression in the red box, right? Now, what are we trying to say? We have our formula for our kinetic energy. We have a formula for our shear stress work rate. If we divide them by each other, we are going to have what we call the kinetic energy rate over the shear stress work rate, right? And then if we simplify and cancel out our units, realize that we are having rho v L over our viscosity. L in this case can be a diameter. So we can have rho Vd over viscosity, which is Reynolds number over 2. Now, it just goes to tell us that Reynolds number has a lot to do with the kinetic energy rate and then the amount of shear stress in the system. Has a lot to do with the kinetic energy rate and the amount of shear stress in the system. So if we have a very high kinetic energy, as we spoke about earlier, then we are going to have a larger Reynolds number. It means we have more turbulence. If we have a larger shear stress work rate, it indicates that we have a larger viscosity, right? And that's going to rather reduce Reynolds number and cause our system to be more laminar. Okay, so in case of fluid flow through a tube, the only possible characteristic dimension L is the diameter. So we spoke about that. That L becomes the diameter if you're moving with a tube, right? And then the characteristic velocity becomes the average velocity. We are using average velocity because we can have different velocities in the system. So we just pick the average of it and then work with that, right? Okay. I think there's something I wanted to mention that I don't think you will need it now. Okay. I think we'll talk about that later. So another interpretation of the physical meaning, we can also see that Reynolds number is our inertial force over our viscous force. Is that okay? So this is another way we can interpret Reynolds number, our inertial force over our viscous force. Is that okay? Okay. So that's it for chapter 2, the introduction to fluid flow and Reynolds number, right? So we move to the next thing we want to consider for today. That's the overall mass balance. So we'll talk about the overall mass balance for a while, and it's very similar to what we did with CPC and then what we did in thermodynamics as well. Okay. But before I continue, are there any questions from what we're talking about so far? Boundary layer flow and boundary layer separation, and then Reynolds number. If there are any questions, you can just let me know. If there are no questions, then I'll just start with this lecture, with this discussion.